Hello friends, welcome back to this series where we work through the book on quantum mechanics by Steven Weinberg. This is lecture 27 and we are at chapter 4 of the book. Let's continue our discussion on symmetries in quantum mechanics. Today we shall talk about the inversion symmetry of a physical system. To be more concrete, we can think of this as a system of particles which could be of different species, all interacting with each other. But before we begin, I would like to encourage you to leave your questions and comments in the comments section if you find any part of this video that is unclear. I'll try to address your questions as soon as possible. With that said, let's continue. Inversion is also more commonly known as parity. Let's see how this is defined. The only defining feature we required of this operation is that it flips the position vector, giving it a minus sign. In quantum mechanics, this is a transformation of the position operator. Let's implement this by the operator pi, which is a unitary operator. This is easily generalized to the case of many particles. We distinguish the different particles by the index n. To be more concrete, let's suppose we have an n-particle system. Let's see how the particles' momenta transform. This can actually be inferred from the transformation of positions. Since momentum is just the velocity of a particle multiplied by its mass. As before, the dot here represents time derivative. If we are only dealing with classical variables, then the minus sign of position would just carry over directly to a momentum, according to this definition. But since we are dealing with Hilbert space operators, let's do this more carefully. Recall that operators evolve in time by the unitary transformation generated by the Hamiltonian. From this result, the time derivative of the position operator is just given by, which is just the Heisenberg's equation of motion. We have discussed this extensively in lecture 4. Let's figure out how momentum transforms under parity using this relation. Applying the operator pi and using its unitarity, we have its action on position is just a minus sign, according to our definition above. And here, to proceed further, we have to look at how the Hamiltonian itself transforms under parity. If we assume that the dynamics of the system is symmetric under parity, this means the Hamiltonian is invariant under this transformation. Thus we see, like position, the momentum operator is flipped by parity. The transformation rule for X implies the transformation for P, given that the Hamiltonian is parity invariant. The invariance of H is also essential if we want to maintain our rules for parity transformations for all times. This is quite reasonable, since H is the generator of time evolution. Let's show this explicitly. This is the parity transformation of X at some arbitrary time. Again, we have used the unitarity of pi. Suppose at t equals 0, we have defined the parity transformation of X by the rule above. Notice that in the time evolution operator, we also have to deal with the transformation of H. The invariance of H is thus necessary to fix the same transformation rule for X for all times. Here's an example of a Hamiltonian, which is symmetric under parity. This is a system of particles that interact through a potential which depends just on the relative distances between the particles. These relative distances are invariant under parity transformation, while the kinetic energy of each particle is also invariant since it's the momentum square. We can also check that the momentum of each particle is really proportional to the time derivative for position by using the Heisenberg's equation of motion. Recall that this is what allows us to deduce the transformation rule for P from the transformation rule of X. Next, we look at how the orbital angular momentum of each particle transforms under parity. This is straightforward. It is simply invariant, since the minus signs from both position and momentum cancels. Now for the total angular momentum. This will include the spin of the particle, in addition to its orbital angular momentum L. How would J transform under parity? To answer this question, we note that J is the generator of rotations for all the observables of the particle. In particular, L itself rotates like a vector operator under the action of J, and so must satisfy the following commutation relation. Recall that back in lectures 7 and 19, we have shown that any vector observable, V, of a particle must satisfy such a commutation relation with the total angular momentum, in order that it rotates like a vector. We can then apply the parity transformation to both sides of this equation. Since L is invariant under this transformation, this means J must also be invariant. The invariance of both L and J means the spin of the particle is also invariant. Thus all three types of angular momenta are invariant under parity transformation. Let's drop the particle indices for now to simplify notations. All the observables in the red box are invariant under parity, except for maybe the Hamiltonian H. For now, we are just studying the cases where H is parity invariant, and assume this to be true. We shall give an example of a parity violating interaction later in this video. Let's now look at the effects of parity transformation on position eigenstates. The rule above leads to the following. And using the unitarity of parity, thus the position state X under the transformation of parity just gives another position state with an eigenvalue of -x. We include a proportional symbol here, since these states are equal to an overall phase factor. This has to be just a phase, since pi is unitary. And we have our result. This is the effect of parity transformation on a position state. We shall discuss the phase factor between these two states in just a moment. For now, they could be treated as equal. Even though we are dealing with a position state here, in general, There could be other quantum numbers describing this state as well. We shall assume that they are parity invariant, and lump them together in a Greek symbol. Now let's look at the effects of parity on the eigenstates of observables that are invariant under parity. For example, the energy eigenstates. H could be replaced by its parity transform. From this, we can deduce that the transformed state share the same energy as the original state. This relation is accurate if we are only interested in the energy of the state. But in general, the situation may not be that simple, since the operator pi may change the other aspects of the state in a non-trivial way, even as it keeps the energy invariant. Our argument can be applied directly to all the other observables that are invariant under parity, like the orbital angular momentum with its eigenstates Lm, the total angular momentum, and the spin states. Now let's discuss the phase factors that may result from parity transformations using the position states as example. First, let's show that the constant of proportionality, eta, is really a phase. This is the consequence of the unitarity of pi. Take the bracket of the transformed state, and using the relation above, we have, by the unitarity of pi, assuming that the position eigenstates are normalized, this implies that the absolute square of eta must be equal to 1. This means eta is indeed a phase factor. This relation has to be true for all times, since we have assumed that Hamiltonian is parity invariant. Let's write the time evolution of the states explicitly. We can rewrite this using the relation above. Since the position state on both sides is arbitrary, this becomes an operator equation, which implies that H must commute with the parity operator. This is just another way of saying that H is symmetric under parity. Thus, for the relation above to be preserved in time, we once again require that H be parity invariant. A reasonable question we may ask is, if it's possible for this phase eta to depend on any property of the state that pi is acting on. For example, if eta is the same for all states, then we could simply redefine the parity operator as pi prime, like so, and set the phase to be 1. However, if eta could depend on the state, then the situation is less trivial. For example, could eta depend on the eigenvalue x for a position state? Well, actually no. Here's why. It is easy to see that any rotation commutes with the parity transformation. This implies that the operator pi commutes with the generator of rotations, J, which is what we have shown earlier. What about the scale transformation D, in which a spatial vector like X is multiplied by a scale factor lambda? It is easy to see that this too commutes with parity. Using a combination of rotation and scale transformation, we can transform the position X into any other position. The rotation R changes the direction of the vector, while the scale transformation D changes its length. Let's apply rotation and scale transformation to the parity equation above. On the right-hand side, the position state minus x is transformed into minus x prime. On the left-hand side, we can use the fact that pi commutes with both scale and rotation. Thus we see that eta x is equal to eta x prime, according to the definition of eta above. Remember that x prime could be any position. Therefore this means eta is independent of position. What then could this phase depend on? Even though this is independent of position, it could still depend on the other properties of the state that are invariant under parity, like the species of the particle. It is helpful to split our state into a product, one which is the part that is transformed non-trivially by parity, like the position state in this case, and the other part phi, which is invariant under parity. We can then consider the effects of parity on each part separately. Since the state phi is invariant under parity, it is therefore an eigenstate of pi, and eta phi can then be seen as the associated eigenvalue. An example would be the eigenstates of orbital angular momentum. But note that in this case, it would not be possible to express this as such a product state, since the orbital angular momentum and position don't commute, and so could not share eigenstates. Phi would then have to be the eigenstate of some other parity invariant observable, but this is just an example. Since we are on the subject of orbital angular momentum, let's see what are the parities of its eigenstates. It is not difficult to see that eta can only depend on L. Let's apply the ladder operator of angular momentum on both sides of this equation. On the right-hand side, we get a different state in the same L multiplet. On the left-hand side, we can use the fact that pi and L commute. By applying the ladder operator, we could get to any state within the L multiplet. And all these states must share the same parity, eta. which means eta must be independent of the quantum number m, although it could still depend on L. Let's now calculate this phase. This can be done by looking at the representation of these angular momentum states in position space. We went through this in details back in lecture 11. You can check out that video with the link in the description if you need a review. The radal part of this function is parity invariant by definition, since it only depends on the magnitude of x. Therefore, all the non-trivial transformation properties by parity is carried in the angular function, which is just the spherical harmonics. X hat here is just the unit vector that points in the direction of x. We know how this transforms under parity from the results of lecture 11. This transformation simply multiplies the original function by -1 to the power of L. Let's apply this result to the above. Insert the parity operators using its unitarity. Pi dagger acting towards its left on x just gives the state -x. Using the result below, the expression underlined blue can be written as, because the effect of adding a minus sign to x can be negated by the multiplication of -1 to the power of L. This is a property of angular momentum wave functions. We can then factor out the position states from this equation, since they are arbitrary to begin with. What's left is the effect of parity on the state Lm, and it shows that Lm is an eigenstate of parity, with eigenvalue -1 to the power of L. This is precisely eta L. Let's go through an example which will illustrate the use of this relation. This is the coupling of an atom to an external electric field through the interaction with its electric dipole moment. The electric dipole moment is the sum of all the positions of the electrons in the atom relative to the positive nucleus, weighted by their charges. Here, only one electron is illustrated. Hi is the interaction Hamiltonian, describing the coupling of this dipole moment to an electric field. This electric field is represented as an ordinary number here, instead of an operator, because we have assumed that it is not quantized. This is appropriate because this field is considered to be macroscopic in the sense that we can ignore the perturbation on it by the back reactions of the electrons, and thus it could be described by a classical field. This classical field evolves in time, independent of how the electrons change in time. Only D is a Hilbert space operator. Hi is inspired by classical electrodynamics. It is Hi that drives the transition of the atom from an initial state to a final state, with the transition probability, or the transition rate, given by what is known as the Fermi's golden rule. We shall derive this formula carefully when we get to time-dependent quantum processes. But from what we already know about the time evolution of quantum systems from Lecture 4, it is not difficult to see why this expression makes sense, since the Hamiltonian is the generator of time evolution after all. Both the initial state and the final state are the eigenstates of the unperturbed Hamiltonian, H0. This is just the description of the atom, where its electrons are bound by the Coulomb potential of the nucleus, without the applied electric field. We are now trying to study the transitions of the atom between the eigenstates of H0 under the influence of Hi. We now look at the parity transformation of Hi with the origin of our coordinate system set in the center of the atom's nucleus. This can be gathered from the parity transformation of the positions of the electrons with respect to the nucleus, which results in the transformation of D. The electric field itself is classical and is thus not affected by the implementation of parity transformation in Hilbert space. Looking at this transition amplitude, we can just focus on the bracket of the operator D. The electric field is just there for the ride. Using the relation above, we can replace D by its parity transform, as long as we add the minus sign. The two states I and F are both eigenstates of parity. This is because they are the eigenstates of H0, which is assumed to be spherically symmetric, and therefore must also be eigenstates of angular momentum, and these have definite parities, as we have just shown. Pi I is the parity of the initial state, while pi F that of the final state. Let's see what are the conditions for this amplitude to be non-zero. According to this equation, the matrix element of D is equal to itself multiplied by this factor. Thus, in order for it to be non-zero, this factor must be equal to 1, which leads to this condition. This is the selection rule that must be satisfied in order for the transition to occur. It is a constraint on the parities of the initial and final states. Now we can use our result of the parities of angular momentum states. Let's assume the simplest case, where there is only one electron in the atom, like the hydrogen atom. As mentioned earlier, the states I and F are also eigenstates of orbital angular momentum. Thus, the selection rule on their parities puts a constraint on their angular momentum quantum numbers, Li and Lf. Bringing the minus 1 to the left-hand side of this equation, we have. This implies that the exponent of minus 1 must be an even number. This is equivalent to the absolute difference between Li and Lf being odd. We can see this more easily by looking at the original condition underlined blue. But now, let me bring up a concerning observation. Notice that since the electric dipole moment d is not parity invariant, Hi is actually parity violating. This implies that the total Hamiltonian H is also parity violating, since we have assumed that H0 is parity invariant. It is also worth noting that this parity violation is not fundamental, since the electric field is not given a quantum treatment and would have been transformed by parity. Since the interaction is purely electromagnetic, it must therefore be invariant under parity at a more fundamental level, because quantum electrodynamics, which is the underlying theory, is parity invariant. But that is a subject for a future video. The essential point is that H should be treated as a kind of effective Hamiltonian, which is parity violating. This brings us to the earlier point, that the parity transformation pi could not be defined consistently throughout all times if the Hamiltonian itself is not parity invariant, since H is the generator of time evolution. Let's quickly run through this argument again. Thus it does appear that we have ran into a contradiction. But actually, we are really dealing with two different Hamiltonians. This has to do with what is known as the interaction picture of time evolution. I can only get into the details of this topic only when we reach the next few chapters of the book, but here's a quick summary. The actual expression for this transition amplitude is actually slightly more complicated, involving a time integral from the initial time 0 to the final time t. And the Hamiltonian that is responsible for the time evolution of all the operators under the integral is actually h0, which is assumed to be parity invariant. h0 generates the time evolution of the atom under its own Coulomb interactions without any external perturbation, while hi describes the perturbation by an electric field which drives the transition process. This is known as the interaction picture. You don't have to get all the details here. All you need to know is that the operators evolve in time by h0, and h0 is parity invariant. This is the way all the operators within hi evolve in time, and we are thus able to define the parity transformation consistently through time. Let's summarize all our results on the parity transformations of operators. These empty slots could be filled by positions, momenta, and angular momenta operators. Consecutive applications of parity gives This shows that the transformation by pi square will leave all the operators above unchanged. This means they all commute with pi square. Note that these are all the operators containing the spacetime information of the particle. They tell us where is the particle and how it moves and rotates. We can call them collectively as spacetime operators. Since pi square commutes with all of them, it must therefore be a non-spacetime operator, which could be associated with some internal symmetry of the particle. Let's write this as e to the power of ia, where a is some non-spacetime observable, the generator of the symmetry. This relation suggests that we could write the operator pi as a product of two commuting parts. The first part is the square root of EIA. This is the non-spacetime part, while the second part is the spacetime operator, pi tilde. This decomposition and the relation in the red box implies that the square of pi tilde is equal to 1. We can apply this factorized operator on the earlier state, which is factorized in the same way. The spacetime operator pi tilde is the one which effects the non-trivial transformation of the position state, which is the defining action of a parity transformation. Here, for simplicity, we are considering the case for a spin-zero particle. Therefore, the spacetime part consists of just the position and doesn't include any spin degrees of freedom, which should belong to the spacetime part. Phi just describes the non-spacetime part of the state. The non-spacetime part forms an eigenvector equation with eta phi as the eigenvalue. This means the state phi is also an eigenstate of the operator A. This implies eta equals. If A is Hermitian, alpha would be real, and we could immediately see why eta is a phase. Since pi tilde is responsible for the non-trivial transformation that defines parity anyway, we simply drop the non-spacetime part and just set the parity operator to be pi tilde. Note that these two expressions implies that pi tilde is also Hermitian. With phi as its eigenstates, what are the eigenvalues eta of pi tilde? Since this operator is Hermitian, eta must be real. Applying the transformation twice, we have which implies that eta phi could either be +1 or -1. We have already seen earlier what eta is for the eigenstates of orbital angular momentum. This could be called the orbital parity. But there could also be another type of parity, unrelated to the motion of the particle. This is the intrinsic parity. Much like how the intrinsic spin is to the orbital angular momentum. This example should serve to illustrate the concept of intrinsic parity. Let's look at the decay of the Deuteron-Pion atom. This is an atom with the positively charged deuteron as the nucleus and the negatively charged pion as the electron. This atom is unstable and could decay into two neutrons through the strong interaction, which conserves parity. The Deuteron-Pion bound state is the 1s state. Remember that this means the pion is in the ground state, with principal quantum number n equals to 1 and angular momentum L equals to 0. The deuteron has a spin of 1 from the composition of two spin-half particles, a proton and a neutron, while the pion has spin 0. Together, the sum of the spins and orbital angular momentum gives a total angular momentum of 1. Basically, only the spin of the deuteron contributes to the angular momentum. This is the initial state. However, let's first make an important point about the orbital angular momentum L. What exactly is this measured against? That is, where do we place the reference point with which L is defined? In the problem of the hydrogen atom, back in lecture 14, this origin is placed at the center of the nucleus. In this case, the nucleus is much heavier than the electron, and thus would not undergo appreciable accelerations through the Coulomb interaction. Hence we can treat it as undergoing a constant motion, and place our reference frame on the nucleus. We have elaborated on this point in lecture 16. But here, the situation is much different. Both the particles in our bound state are much closer in mass, and for the final state with two neutrons, they have in fact identical masses. So where should we place our reference point? If we were to select just the lab frame, then it means describing a two-particle state. But we have not yet learned how to describe the orbital angular momentum state of a two-particle system. What would the quantum number L mean in this case? But as we are going to show, this problem has an effective single-particle description. L is actually associated with the total orbital angular momentum of the system measured in the center of mass frame. Let's look at a general two-particle system. X measures the position of particle 1 with respect to particle 2. The center of mass position of the system is defined in the usual way. Capital M is the sum of masses. Let's change variables from x1 and x2 to x and xcm. We denote the mass ratios by the alphas. Thus we have x2 in terms of x and xcm. Substitute this result back into the expression for x1. From the definitions of alphas, this factor is just alpha 2. Let's calculate the total orbital angular momentum from these results. The velocities of particles 1 and 2 are given by Let's expand out this cross product. The second cross product is obtained simply by making these replacements of parameters in the first cross product. From the definition of the alphas, this term is 0. This term is called the reduced mass. Thus we see that the total orbital angular momentum can be broken down neatly into two parts, one due to the center of mass motion, and the other the relative motion of the pair of particles. If we place the origin of our reference frame at the center of mass and go into the center of mass frame, we find that the cm contribution vanishes. This is possible because the cm velocity is constant, since we are assuming that the only forces present are those that are acting between the two particles. Hence the total force in the system is 0 due to Newton's third law, and the cm doesn't undergo acceleration. And the total orbital angular momentum of the two-particle system can be described purely in terms of their relative motion, which is represented by x. Thus our system reduces to effectively a single particle system described by this coordinate. Let's find the momentum that corresponds to x, such that they form a pair which satisfies the canonical commutation relation. This is necessary for their quantization. Intuitively, this momentum should be the velocity multiplied by the reduced mass. Let's check that these really satisfy the canonical commutation relation. we can use the commutation relations of the original variables. A and B are the particle indices, labeling particles 1 and 2. Indeed, X and P really form a conjugated pair. From here, we could directly quantize the angular momentum associated with X and P. This has the significance that the angular momentum states we find would correspond to the total orbital angular momentum observed in the center of mass frame. We can just use our previous results. The quantum numbers L in the orbital parities thus correspond to the relative angular momentum of the two-particle system. We can deduce the effect of parity transformation on X and XCM from the transformation of the original variables. XCM is invariant in the center of mass frame, while X transforms under parity in the usual way by a minus sign. Going back to our problem of the Deuteron-Pion atom. Recall that we have just finished our analysis of the angular momenta of the initial state. Now that we have a good understanding of the orbital angular momentum L, let's look at the final state. Let's first look at the total spin state of two neutrons. Since neutrons are spin-half particles, a two-neutron system has total spin of either 0 or 1 by the usual rule of angular momenta addition. Spin 0 corresponds to a singlet state, which is anti-symmetric with respect to the exchange of particles. Spin 1 has a triplet of states, which correspond to different angular momentum projections along a chosen axis. They are all symmetric under particle exchange. Now we look at the orbital angular momentum state of the two neutrons. Since neutrons are fermions, they must satisfy the Fermi-Dirac statistics such that any quantum state must be anti-symmetric under the exchange of two identical particles. Thus, the orbital state must form a product with the spin state such that the total state will be anti-symmetric under particle exchange. This means the anti-symmetric spin state must pair with a state which L is even. We claim that such orbital states are symmetric under particle exchange. This is why. Let's go back to the earlier relations between X and XCM and X1, X2. For the case of identical particles, M1 is equal to M2, which implies that alpha 1 and alpha 2 are also equal. This means that under the exchange of particles, which is just switching the labels 1 and 2, XCM is invariant. Whereas X is transformed by a minus sign, this is exactly the same as its parity transformation. Therefore, states with even orbital parity must also be symmetric under particle exchange. And these are the states with even L, which is what we have set out to prove. By the same reasoning, odd values of L would then be anti-symmetric under particle exchange. To form a total anti-symmetric state, the spin 1 states must pair with the orbital states with L equals odd. Conservation of angular momentum in the decay process demands that the total angular momentum of the two neutron state must also be equal to 1, same as the initial state. Let's examine the spin zero branch to see if we can find any state which satisfies this constraint. By the rules of angular momenta addition, S0 and L even can only lead to a total angular momentum of J equals L, which is even. This violates the constraint. These are the possible total angular momenta. We see that for L equals 1, which is odd, the J equals L solution is the only one that satisfies the constraint. Therefore, the parity of the final state is given by, which is just the orbital parity, multiplied by the square of the intrinsic parity of the neutron. For the initial state, since L is 0, we need to include only the intrinsic parities of the deuteron and pion. Conservation of parity then gives us this equation. This equation relates the intrinsic parities of all the particles involved in the decay above. We can break down the intrinsic parity of the deuteron further, since it is composed of a proton and a neutron. It turns out that this is just the product of the intrinsic parities of these two particles. The reason why the orbital angular momentum between the proton and the neutron doesn't contribute to this parity is because its only allowable values are even. This has to do with the details of the deuteron bound state. We shall not go into the details here, but it has to do with the spin dependence of the nuclear potential binding these two particles together, their isospin state, as well as the requirement that we get a stable bound state. We can view the situation this way. Suppose the deuteron is produced by colliding together a proton and a neutron, which are initially traveling as free particles. Since the strong interaction that is responsible for forming the bound state is parity conserving, the parity of the final and considerably complex state of the deuteron must still be equal to that of the initially free particles, which state is simple. And their total parity can only come from the intrinsic parities of the particles, and that due to their relative motion, which is quantified by L. This is why, even when talking about the parities of bound states, we can simply consider the parities of the constituent particles and their quantum number L. Since the orbital angular momentum of the deuteron bound state does not contribute to its parity, let's just plug in these intrinsic parities into our equation. Here there's a cancellation. Thus we now have a relation between the intrinsic parities of the pion and the nucleons. Recall that earlier we have separated the parity operator into two commuting parts, a spacetime part and a non-spacetime part. We have opted to keep only the spacetime part, since it is sufficient to satisfy the defining property of a parity operator based on the transformation of spatial operators like the position vector. This means pi tilde will commute with all internal transformations, including the isospin symmetry. This topic is covered extensively in Lecture 26. See the link in the description. This is the symmetry where the proton and the neutron are treated as different states of the same particle and form an isospin doublet. The symmetry must necessarily be approximate, since these two particles have different masses and electric charges. The isospin symmetry transforms a proton into a neutron and vice versa. This fact will be useful, since it allows us to show that the parity of the proton is in fact equal to the parity of the neutron. Pi tilde commutes with all the isospin generators, and therefore also with the isospin ladder operators, T plus minus. Recall that the proton is the highest weight state in an isospin doublet, and T minus lowers it into a neutron state. Let's apply the parity operator on both sides of the equation. And using the fact that these operators commute on the left-hand side, pi acts directly on the proton state. Thus we see that the isospin being parity invariant implies that the proton and the neutron have the same intrinsic parity. This result is quite general and applies not just to this nucleon doublet. All the members of any isospin multiplet must share the same intrinsic parities. We can apply this relation on the Deuteron-Pion atom decay, which means the nucleon parities cancel. This gives the intrinsic parity of the pion. However, it must be noted that the isospin symmetry on which this result depends is only an approximate symmetry in the strong interaction. There's actually a way for us to derive results like that in the blue box using exact symmetries. The symmetries are those involving the conservation of electric charge, baron number, and lepton number. These are the exact symmetries of the standard model of particle physics, which as far as we know, governs the behavior of the most elementary particles in nature. The baron number counts the number of particles which are made up of 3 quarks, while the quarks themselves have baron number of 1/3. For example, the proton and neutron both have baron number 1. The lepton number counts the number of electrons and neutrinos. These particles have baron number 0. An elementary particle can either be a baron or a lepton. We now show that using these symmetries, we can modify the definition of the parity operator such that the intrinsic parities of the proton and the neutron could be set to the same value. We do so by appending to pi tilde an operator that is -1 to the power of some linear combination of the 3 conserved quantities above. Alpha, beta, and gamma are real numbers. The new parity, pi tilde prime, will then have equal eigenvalues for the proton and the neutron. Note that Q, B, and L are generators of internal symmetries and therefore should commute with pi tilde by definition. So we could place this factor on either side of pi tilde. Suppose initially for pi tilde, the parity of proton is equal to 1, while that for the neutron is equal to -1. The two are not equal. For which choice of alpha, beta, and gamma could we set both of these numbers to 1? It is not difficult to see that this new definition of parity will give us the desired result. On the other hand, if these are the initial values of the proton-neutron parities, the following definition of parity will again set both parities to 1. And for the third case, we could do it with this redefinition. Thus we see that the parities of the proton and neutron could both be set to 1 by appropriate redefinitions of the parity operator for all possible cases. But notice that up till now, the particles we are talking about have baryon number equal to 1 and lepton number 0. We have not actually made use of the lepton number operator. We can use this to also set the parity of the electron to 1. Let's see how the redefined parity operator acts on the electron. Start with the case where the parity of the electron equals to -1. For the first case, pi tilde prime gives a new electron parity of 1. This is exactly what we required. And it is easy to see that the second case is also okay. For the third case, since B equals 0 for the electron, its parity remains equals to -1. Thus we will need a new redefinition of the parity operator without compromising our previous results for the proton and the neutron. We can do this by using the lepton number operator. Including the operator L would not affect our results on the nucleons, since these are not leptons, but would set the electron's parity to 1. Now let's look at the case where under the original parity operator, the parity of the electron is already 1. Would this be preserved under these previous redefinitions of the parity operator, which are made to set the nucleon parity to 1? For the first case, acting on the electron, Q is -1 and B is 0. Thus pi tilde prime acting on the electron would give a parity of -1, spoiling the original result. Once again, in order to fix this, we need to include the lepton number operator. This will preserve the parity of 1 for the electron. The second case would also change the electron's parity to -1. But this could also be fixed by including the lepton number operator. Now for the last case, it is apparent that this will preserve the parity 1 of the electron. Thus we have shown that by choosing the appropriate linear combination of the charge, baryon, and lepton number operators in the prefactor of parity, we could set the parity of the proton, neutron, and electron all to 1. The parities of the rest of the particles can be deduced from parity-conserving processes, like how we deduce the pion parity from the decay of the Deuteron-Pion atom. Knowing the parity of pi minus, we can once again use the fact that the parity operator commutes with the generators of isospin symmetry to deduce the parities of pi naught and pi plus belonging to the same isospin multiplet. Pi naught is a step up from pi minus within the multiplet, while pi plus is 2 steps above. Applying the parity operator to these relations and using the blue box, pi tilde acts directly on the state pi minus, moving past the raising operator t plus. This implies that the parities of pi naught and pi plus are both equal to that of pi minus. Once again, This is the result of the isospin symmetry of the strong interaction. But as we have said, this is only an approximate symmetry. So how could we come to any definite conclusions about the parities of these states? What we meant by the isospin being an approximate symmetry of the strong interaction can be made more definite in this way. The commutator between the strong Hamiltonian and the isospin generators are not exactly zero, but close to it. But nevertheless, the three particles, pi plus minus and pi naught, are still the eigenstates of Hs. It's just that when we apply the raising operator to the state pi minus, we now have other than pi naught as the main component, some small corrections. We can view the right-hand side as an expansion in the eigenbasis of Hs. N is the normalization factor associated with the raising of pi minus to pi naught. It is important to note that the parity operator still commutes with the isospin generators, because one is a spacetime operator and the others are not. We shall make use of this in a minute. Let's apply the parity operator to this state. This is equal to, where we have used the fact that pi tilde commutes with t plus. Because the parity operator commutes with Hs, all the eigenstates of the strong Hamiltonian are also parity eigenstates. Thus, what this equation shows is that all the states in this expansion have the same parity as pi minus, including pi naught. In a similar way, the state that is two steps above pi minus is pi plus, modified by some small corrections. Here we have neglected the normalization factor for pi plus, since it is not relevant to our discussion. Applying the parity operator to this equation, and using the blue box, we have Again, this implies that the parity of pi plus is equal to that of pi minus. Thus, we have shown that all the particles in the pion isospin multiplet are equal, even though the isospin symmetry is only approximate in the strong interaction. Now let's return to the ordinary atom and examine how an electron is described in a bound state. An electron state in an atom is usually described by three quantum numbers, the principal quantum number n, which labels its energy, the orbital angular momentum L, and the total angular momentum J. Amazingly, these three quantum numbers remain good quantum numbers, even after we include all the other corrections to the simple hydrogen atom model, H0, which only considers the Coulomb interaction. There could be all sorts of other interactions, like the spin-orbital coupling, the relativistic effects of the electron, as well as the more subtle effects like Lamb shift, which is due to the quantum vacuum of the electromagnetic field. H0 is the simplest and most symmetric model, while the successive corrections tend to reduce the overall symmetries of the Hamiltonian. Even so, if we consider all these corrections to be due to the internal interactions within the atom, then it is reasonable to assume that the total Hamiltonian still possesses rotational symmetry. Since quantum electrodynamics, which governs the forces that bind the electron to the nucleus, doesn't have a preferred orientation. Not unless if there is an applied external field which breaks this symmetry, like in our earlier example on the electric dipole moment of the atom. Therefore, we may still expect the total angular momentum J, which is the generator of rotations, to commute with h. But what about the orbital angular momentum? How can we be sure that this will still commute with h after adding all these additional effects, and so retain L as a good quantum number? For a given value of J, and the fact that the electron is spin half, here are the possible values of L by the usual rules of angular momentum addition. Thus, the simultaneous eigenstate of energy and J must live in the subspace on the basis of these two states. Note that there will always be an energy degeneracy due to the rotational invariance of the Hamiltonian. All the states M associated with angular momentum J have the same energy. For much of our discussion, we shall hide this quantum number, since we have shown earlier that the parity of a state doesn't depend on it. Let's quickly show why these two values of L are the only possibilities. From the usual rules of angular momentum addition, we know the possible values of the total angular momentum J, given L and S. We have derived these rules in lecture 21. For spin half, this leads to these two values for J. They are separated by 1 unit of h bar. Let's represent the J's by a white stroke, while L sits exactly in the middle, separated from the J's by half a unit. L's are represented by a blue stroke. Thus, we can see that if we fix the value of J, there are only two possible values of L, which when combined with S equals half, according to the above rule, contain this possible value of J. These are precisely the values of L listed above. So up to this point, we can only conclude that an energy state of an electron within an atom is some superpositions of two states of different orbital angular momentum. In order to proceed further, we need another property of quantum electrodynamics. This is the fact that it is exactly symmetric under parity transformation. We shall not demonstrate this here. This is a subject for another video. For now, let's assume this to be true. An important consequence of this is that states with definite energies can also have definite parities. Now, we introduce another essential ingredient to our argument. Just to remind you, we are trying to show that, in spite of introducing many complicated corrections to the Hamiltonian to model a real atom, its eigenstates must still be simultaneously an eigenstate of L. It is just these corrections that complete our argument. The key point is that including enough of them will break the symmetry of the highly symmetric H0. This will break the degeneracy of the energy states. The only symmetries of H left after all these corrections are rotational and parity. The degeneracy of energy is broken in such a way that different irreducible representations of rotation and parity symmetries, labeled by J and eta, cannot have the same energy. Otherwise, if two such representations have the same energy, we could then have some extra symmetry which mixes up the states between these two representations, but leaves the energy unchanged. This residual symmetry would be neither rotation nor parity. What we are going to assume here is that by introducing sufficient perturbations to H0, the only symmetries left for H should be just rotation and parity. You can learn more about the irreducible representations of symmetries in Lecture 23 and 26. The links are in the description. In this way, a state with definite energy Nj must also be an eigenstate of parity, since no two states with different parities can have the same energy. These two states, which could have made up the state Ej, have different orbital angular momentum. But these correspond to different parities. Therefore, the state Ej must be equal to just one of these states, in order to be a parity eigenstate. Thus, we have proven what we have set out to prove. The energy state of an electron in an atom must also be an eigenstate of J and L, despite the complexity of the Hamiltonian. We now look at the discovery of parity violations in elementary processes. In the early days of quantum mechanics, it was believed that the parity symmetry is a universal symmetry of all the fundamental laws of nature. This was certainly true for the theories of classical physics which were dominant in that period, for example, the Newtonian mechanics of particle interactions and the Maxwell's theory of electrodynamics. The first suggestion of parity violation came in a series of events in cosmic rays experiments. Highly energetic particles coming in from outer space collided with our atmosphere and cascaded down in a shower of particles. This is nature's version of a particle accelerator. Among all these events, it was observed that two particles, which are similar in every way, appear to decay in very different ways. One of the particles, theta, was observed in 1947 to decay into pi plus and pi naught, while later in 1949, the other particle, tau, was observed to decay into 3 pions in two different ways. These two particles are equal in mass, spin, and electric charge, as well as lifetime. Why two similar particles can behave in such dissimilar ways became known as the tau-theta puzzle. Since we already know the intrinsic parities of the pions from earlier, let's work out the parities of these two particles from their decay products, assuming first that parity is conserved. Later, we shall see that being unable to consistently assign an intrinsic parity to a particle is an indication of parity violation. To begin, let's first note that the spins of both particles are zero. In their center of mass frames, the orbital angular momenta of these two particles are also zero. These imply that both particles have zero total angular momenta. As for the decay products, the pions, they are also spin zero particles. Thus all these states have total spin of zero. By the conservation of angular momentum, the total angular momentum of the final states must also be zero, same as the initial states. This, together with total spin zero, implies that all the final states must also have zero total orbital angular momentum, which means we only need to consider the intrinsic parities of the particles, making this a particularly simple case study. From our earlier results, the intrinsic parities of the charge and neutral pions all have the value of -1. This means theta decaying into 2 pions should have a parity of +1, and tau decaying into 3 pions has a parity of -1. It turns out that these two particles have different parities, which means they should be different particles if parity is conserved in these processes. On the other hand, regarding all the other properties, theta and tau appear to be the same particle. This Gordian knot was finally cut in 1956 by two theoretical physicists, T.D. Lee and C.N. Young, who abandoned parity conservation in these processes and simply assumed that these two particles to be the same particle, now known as the Coulomb. These are the first indications that parity symmetry is not the universal symmetry of nature. The fundamental interaction between these processes is the weak interaction, and unlike the strong interaction, which we have been studying up till now, it violates parity. These weak decays occur over a characteristic time scale of 10 to the power of minus 8 seconds. This is very much larger than the time it took for processes that are driven by the strong interaction. We can estimate the time scale of strong processes by using the rest energy of the Coulomb, since this particle is produced by the strong interaction. This is proportional to the oscillation frequency in time, and inversely proportional to the time it took to produce a Coulomb. This gives a characteristic time scale of 10 to the power of minus 24 seconds, a much faster process. This great disparity in time is one of the clear distinguishing features between the strong and weak interactions. One is associated with parity conservation, and the other its violation. In this example, we can see that if an interaction is parity violating, then we cannot assign parities to the particles involved in a consistent way. We now examine other forms of inversions in the interactions of elementary particles and see how they are related to parity. One of them is charge conjugation. We implement this with an unitary operator, UC, which transforms a particle into an antiparticle. The antiparticle is identical to its particle counterpart in every way, except with all its charges inverted. Apart from the electric charge, these include also the baron and lepton numbers. This next inversion is qualitatively different from the other two. This is the time reversal transformation. We have developed this in details way back in lecture 6. See the link in the description. This time reversal is implemented by this operator, U bar T. More about this operator in a minute. The normal time evolution proceeds as follows by the time evolution unitary operator generated by the Hamiltonian. As we have shown in lecture 6, the state transformed by time reversal will evolve in the opposite direction to how the untransformed state would evolve. In that video, we have also shown that the operator U bar T has to be an anti-unitary operator in order to implement time reversal. An anti-unitary operator is similar to its unitary counterpart in the sense that its Hermitian conjugate is also its inverse, except an anti-unitary operator is anti-linear. This means acting on a linear superposition of states, we need to take an additional complex conjugate on the coefficients of the superposition. That is what we mean when we say that time reversal is qualitatively different. The parity transformation we have spent much of this video studying is also an unitary symmetry, and is the symmetry of both the strong interaction and electromagnetism. Let's change its notation to match the other two symmetries. And as we have just shown, the weak interaction violates parity. Charge conjugation and time reversal symmetries are also satisfied by both the strong interaction and electromagnetism. And it can be shown that all relativistic quantum field theories which are theories that combine Einstein's special relativity with quantum mechanics, must satisfy the combined transformation of all these symmetries. The order of the transformations doesn't matter. This is known as the CPT theorem. We shall derive this result in a future video when covering quantum field theory. The underlying theories of the three fundamental forces of nature are all quantum field theories, and thus must satisfy the CPT symmetry. As for gravity, the jury is still out for its quantum theory, and thus its status under this symmetry is uncertain. Although if this is based on the quantization of Einstein's general theory of relativity, the CPT symmetry is generally agreed to hold true. We have demonstrated the parity violation of the weak interaction. But in fact, it also violates the charge conjugation and time reversal symmetries separately. Very often, it is not easy to test these violations individually, but easier to test them in combinations. For instance, it has been demonstrated in experiments that a weak interaction violates a combination of parity and time reversal. But from this, and the fact that the theory must be symmetric under CPT, we can deduce that charge conjugation is violated separately by the weak interaction. This is how. Let's insert a pair of identity operators into this relation in the form of UC dagger. Notice that the inner tree transformations is the CPT, which is the symmetry of the weak interaction. Recall that the order in which they are applied doesn't matter, so we could replace this by the weak Hamiltonian. Thus we see that the PT violation by the weak interaction implies that it also violates charge conjugation, assuming that it satisfies CPT symmetry. We can rewrite this in a form that is similar to the parity relation above by using the unitarity of UC. Experiments also reveal CP violations by the weak interaction. This would imply time reversal violation. Inserting U bar T dagger into this relation, and using the CPT symmetry. Thus CP violation implies T violation.